In this video I will cover some new topics and some old topics that I was not aware of or didn't understand last year. So we'll do that for a couple of weeks. This week we'll talk about new things in convolutional neural networks. And there are three different things I want to cover. One thing is to look at the state-of-the-art convolutional neural networks, for example on ImageNet. What kind of developments in the architectures have we seen to improve on the ImageNet performance. And the next topic I will cover is image segmentation. I think this is an important topic because image segmentation will be important in autonomous driving and in medical imaging for diagnosis and so on. Then I'll also talk a little bit about new activation functions and mention some of them that are kind of fused together with some of the new developments, especially in convolutional neural networks. So the first three different types of variations on convolutional networks are called residual networks, dense networks, and wave nets. So I'll start out with talking about residual networks, or just ResNets. The first observation that they do in this ResNet paper, and the references are in the last slide, is that it's actually quite hard to train a very deep network. So what they have shown here in these graphs is iterations on the x-axis and the training error in the left graph and the test error in the right graph as a function of the number of iterations. And you can see that you have this progress in both, but that actually if you look at the deepest network that we kind of believe would be potentially be the best performing network with 56 layers, that is actually stuck in both a high training error and a high test error. Here we measure that as the accuracy of the network. And it goes a little bit better with a 20-layer network. So this is a little bit counter what we believe, that we actually believe that more layers are good. So it's something to do with optimization, that we simply cannot optimize these very deep networks. And this is understandable in a way because you have to backpropagate a gradient through a lot of layers, and you start out with random weights, and it's very easy that they get stuck in some kind of suboptimal solution. So what they propose in ResNets is this very simple way of having a bypass layer. So if HL denotes the hidden representation of the feature maps in the Lth layer, then now we'll decompose that into two. We'll have a function f, which is this kind of ResNet block consisting of some convolutions, ReLU, and some more convolutions. Or another variation where we have first some 1x1 convolutions, and then ReLU, and then 3x3 convolutions, and then ReLU, and then 1x1 again. And then we have another term which is simply a copy of the previous layer's hidden representation. So you can imagine that you can kind of consider this thing f is like a ResNet block of computation, right? So that is something you can insert, and you can kind of only count the layers by counting the L index. But the nice thing about having this bypass layer with this L-1 term is that if initially our f function is quite close to 0, then our network is quite close to implementing a linear network. And this means that we can actually start first learning the more linear features, and then slowly we can make f different from 0 and then turn on the feature maps that we need. And if we do this procedure, then you can see this kind of result where we have now we look at the ImageNet results, so it's not the same scale, I guess. So we have just with iterations here, we get on the training side no, that's not true. The left-hand plot is kind of regular network without these residual connections, and then on the right-hand side it's the ResNet connections. You can see now that actually the deeper network has the better test performance in this case. So it works. And actually ResNets, we'll see that later on also when we talk about image segmentation. It's actually giving new state-of-the-art results in both ImageNet and other applications. So here's just a table of the different performance, and you can see that you can actually go up and get the best performance by a ResNet with 152 layers, so that's quite impressive. So now we're really talking about deep networks. And also I think this is the state-of-the-art ResNet, 3.6% and 3% error. So there's also another variation of the same theme, which is called dense nets. The idea there is that you kind of use the previous layers within what is called a dense block as kind of like a feature bank, so to speak. And then you connect, when you have layer L, you can actually use the feature maps from the previous layers. And it's a little bit like ResNet, so if you compare the two formulas. So the way to avoid, because this looks like you have a lot of parameters, because now you actually, if you have layer L, you connect that to L other layers, right? If you count from 0, then you have a lot of parameters and a lot of connections. And the way that we actually avoid parameter explosions, and I've shown that on the next slide, is that we have very few feature maps in each of these layers. In that way, we kind of avoid explosion of parameters. And then another way, I'll come back to that actually on the next slide, but that's also shown in this figure, that we have these kind of transition layers that consist of convolution and pooling between, and in that way we can actually kind of now diminish again the number of feature maps. So here's a little bit of back of the envelope calculation. So if we have L layers, for example 5 in this figure, and we have this growth factor which we call K, which is just the number of feature maps in each layer, then since a feature map is connected to all the previous layers, then layer L in this block has L times K channels that is directly connected, and each of them comes with for example, 3x3 filter. So that means that we have something that scales like L squared in the number of filters that we connect to in a given layer, or in all the layers. And this should be compared to something that only scales with L in a standard calculation. But if we keep this K, this kind of growth factor, number of feature maps in each layer, small, and we also use these transition layers that they consist of 1x1 convolutions that will give us an ability to diminish the number of feature maps, and we then use pooling to get a smaller image, then we can actually keep the parameters in check. So that was dense nets and ResNets. The last, I have another slide just to kind of sum up the development in this convolutional race with getting better and better image net performance, and also other better performance on other image classification tasks. This is a famous AlexNet, so it made 16.4% error in the top 5 on ImageNet. It has 8 layers, and in order to make one prediction, you have to make 1.4 gigaflop floating point giga floating point computations. And with the ResNet, you have 152 layers, and you have to perform 16 times as much computation. So this means that actually maybe kind of in the old days we believed maybe that the reason why we didn't get so good performance in our models was because we used the wrong models, but I think this example more shows that maybe we actually used too small models, because of course we didn't have the fast computers back then. This is yet another net variation on the convolutional idea. Now we are actually working with time series, and this is a small GIF I got from the DeepMind blog. So that shows how this works. And this is these convolutions you see here is so-called dilated causal convolutions. And causal means that we actually want to predict from a time series. We want to predict the next time step, or it could also be another sequence than a time series. And we do that by actually using the paths, right? So that's what kind of indicated kind of this path of computation. And dilated means that we kind of remove some of the connections. And the reason why we want dilations is we want to build a network that is not too large, but a network that can look far into the past. And we can do that by actually having this kind of doubling factor, as you can see in the animation. Right, so for each extra layer we put, we look double as much back in the past. It turned out that these models can actually make very nice performance on something like speech synthesis and so on. You can check that by the link. But they actually, it's a little bit hard to fit on data, and they can also become quite slow because they use a lot of layers of convolution. So that leads me to the discussion of how to actually design a specific activation functions to deal with this.